Hey guys, welcome back to another episode of Simulio. So today, we're going to be covering one of my favorite algorithms ever that we have already covered on this channel. I'm sorry about that, it's just, we covered it like 2 years ago, so I kind of feel like it's not that big of a deal to do it again. But yeah, so we're finally going to be doing Huffman Encoding on the algorithm archive in YouTube. So I figured let's go back through, let's write up the code that we need for the algorithm archive article and go from there. So yesterday, I spent a good amount of time going through and talking about, let's go here, algorithm archive. I don't know why it says convolutions, but here's what I want. Maybe I just Googled it at some point. That is actually not what I want. Let me just go algorithm archive. Get book. Oh, sorry for the yawn. And if we go to read, we will see that we have a new thing down here for data compression. So the next thing that I wanted to do was talk about Huffman encoding, talk about data compression a bit, and talk about basically what Huffman encoding is, why it's interesting, why data compression is cool, all that kind of stuff. Oh, well that's super interesting. 1 second. Shoot. I have to do something real quick. CD projects, algorithm archive, ls cd chapters, data compression, ls, vi huffman.md. This header I need to put into vi data compression.md because otherwise the math doesn't load automatically. So let me just do git add data compression.md get commit -m adding math text. I guess auto rendering method, and we're gonna do git push origin, and I guess it's just gonna be master. So now it's available for you guys. And that should be good. So that's one thing I don't like about this whole Gitbook thing. It's kind of finicky at times, especially for all the things that like LaTeX does very well. But hey, it is what it is, you know? There's really nothing I can do about it. I guess while we're waiting on people to come in today, again, I'm not really sure how many people will be coming in today because I did stream on Friday, then I took a few days off again for the weekend. It's kind of one of those things. And it's also Easter Sunday, so maybe some people are celebrating Easter with their family. I don't really know. But that's okay. So what I wanted to talk about was something I noticed over the weekend. How do I put this? You guys know 3 Blue 1 Brown, right? It's like a massively successful mathematics channel on YouTube, and that's something that I kind of find really weird. I mean, it's a channel fundamentally based off of the elegance of mathematics, and I find it weird that it's such a successful channel. Not necessarily because it's a bad channel. It's a pretty good channel, but it's weird that it's so successful when it's founded around an idea that's fundamentally not interesting to a majority of people. And by that I mean it goes against the status quo. I mean, like, if you were to tell me 2 or 3 years ago that a channel based exclusively around mathematics that is meant for people who already have an undergraduate degree would be doing well on YouTube, I would have thought that'd be really weird, because who watches that kind of video? I mean, it's not, I mean, heck, I don't even watch those types of videos that often, and I'm in the target demographic, you know? Like, now I don't watch the videos because I kind of enjoy reading articles a little bit more, and I don't know if that's necessarily true for most people, but I would say that it is weird that we have a channel that's so incredibly popular based off of such a not obscure, but different topic. Hey, Gathros. So I was thinking about it, and I was kind of looking at a whole bunch of different people's, you know, paths to success. I mean, there's a lot of very good people out there, on YouTube. You know, for science educators, you have 3 Blue 1 Brown for math. You have Minute Physics, and of course Minute Earth. You have a bunch of different people like that. So obviously you have Veritasium, Smarter Every Day, Vsauce, all these people. And they're all very good. I mean, they're all very good channels. But the thing is, Vsauce, the reason he's popular is because he's able to take a topic that is, you know, maybe not particularly interesting, and then he presents it in such a way that it becomes interesting. The reason he's popular is because he's a fantastic editor. His videos are very well polished, and they make it so that when he's speaking, he sounds interesting just because, well, you know, he has a way of presenting his topic. You know, he has a good script, he has good editing. That's kind of the main thing. Veritasium does it kind of a little differently. He has more of a business around it. He kind of takes things that he thinks people are interested in, and he just immediately starts talking about that kind of stuff, you know? And that's cool, don't get me wrong. But I don't know. His channel is again one of those channels that is very easy to see why people like it, because he's covering topics that are interesting, like in a sense clickbaity, you know, like he's covering stuff that people would be interested in. And Smarter Every Day kind of covers channels or covers videos that are interesting anyway, you know, like he is interested in them, so he figures other people will be interested in them, and that's kind of the way it goes, you know. But 3 Blue 1 Brown is fundamentally different. It's interesting because, I don't know, it's interesting to me, it's interesting to a whole bunch of other people who are like getting PhDs, but I didn't think that demographic was large enough that he'd be able to make a super successful business out of it. But apparently it is, and so that's been kind of motivating for me over the weekend. I was thinking about it, and I was like, you know what? I've got a very weird community. It's a community of people who are willing to watch a programming stream for an hour every day or something like that. It's a community of people who are willing to contribute to a book on algorithms for fun. You know, it's a group of people who, I don't know, just will spend hours and hours every day just kind of messing around with some code just because that's what they like to do. It's very interesting. And so what I realized is I don't know if my target demographic is large enough to necessarily, I guess, make it online. You know, like I don't know if it's large enough to create a community that can sustain me via Patreon or something like that. I just don't know. But I did want to say that maybe there is hope for that to happen. And I don't know if I necessarily want to, do this whole thing full time or not. I've been thinking about it a lot recently, as you guys know. But I would like to at least devote some time to writing the algorithm archive full time, whether it only be for a month, or it be for a year, or it be for all eternity. This is kind of, I don't know. But I don't really have any really big projects on the purview besides the algorithm archive. I mean, like, for example, if I was doing this project full time, I'd probably be streaming way more frequently. And what I would probably do is I'd probably try to do like a Zeldathon-esque hackathon, you know? Because I thought I really like hackathons, and I think it'd be kind of fun just to get a whole bunch of popular streamers together and just kind of do a hackathon together. You know, I think that'd be a lot of fun. And I think it'd be watched relatively well, maybe not so well, but I think it'd be a good kind of movement for that community. IVL, that's the thing. I need to think about this kind of stuff. I'm sorry about that. As far as the visualization is concerned, I'll be working on that again. But Gathros, you've been doing a lot with it recently, and I'm not sure how to proceed, honestly, from here. So I need to kind of figure out the best way to go from there. I want to also give another engine a chance that I've only recently been made aware that it actually works on Linux. So I want to just give it a shot, take a look at it over this week, see what it can do. Because it can apparently do 2D and 3D animations just fine, also render to video, do OpenGL stuff. It seems to be able to do everything I want it to be able to do. And Happy Little Rat and Gustorn were not particularly happy with Cairo the other day. And they're kind of like the big folks in the community that know what they're talking about. So if they know what they're talking about, I don't know what I'm talking about. Let's kind of take a look at some other stuff too. But that's how it is. I made tree traversal in Gathfiel. Let me see. Open link. Source. Multi-animations.cpp. 1 second. This test.cpp. 0 to 49. I have to take a look to see what that means. And what MA. Multi-animator. Let me take a look at what this sent. Let's do. I actually haven't checked it out yet. Sorry about that, Gathros. Clone. Grab this guy. Pop over here. CD. Let's do ... One more time and one more time, and let's go ahead and do git clone. Pop this. Okay. Git clone. And let's see what we got. Okay, we're going to cd into gathvl. Run a quick ls. Then I should just be able to make run /viz test. Now let's see what happens here. ls temp maybe. Okay, so let's do a quick mirage image. Temp. Image 000.200.png. Oh, that's not bad. Yeah, okay, I'm a fan. There's some stuff that you need that I do with the animation to make it just a little snappier when I'm doing this type of stuff. Like I'll make it so that the the image gets slightly bigger and then kind of fades back, so it kind of bounces in and out. Here, I'll show you what I mean by that in just a second. So like for example, when I go into cd /cd ls, and let me go into, is it in KaiVL? I don't think so. I think it's in Simuleos and then Euler. And let me see, what do we have here? I think if I just run /Euler, it'll generate something. I'm not sure what, but it'll take a look. Give it just a second. Okay, so it's doing something. I'm not sure what again. Should probably have taken a look to see what it was doing before generating the images here, but I didn't do that. So I'm just hoping that this is doing something interesting. I have no idea what I'm doing. Yep, 1 second. I don't know what visualization this is running at all, but that's okay. 1 second. What is it doing? What were the visualizations we had to do for the, Oh, I know what it's doing. This is not the one I wanted either. Darn. Oh, well, I can show you guys this visualization because it's cool anyway, but in case you didn't see the Euler method video, it's pretty cool. I'm a fan of this one. Do a quick ls in temp. It looks like... Oh, I know what it's doing. It's rendering all of them to images, I think. Yeah, give it a second to do that. Takes a while because of the way that I ran this. That's my bad. What's the library you were looking at? What do you mean what's the library I was looking at? I'm looking at a mixture of my... So, here's the thing. As far as KaiVL is concerned, I am nowhere near done with KaiVL on my end. Like, I basically just started it, opened it up for 2 days, and then I kind of stopped. And obviously there's a bunch of reasons for that. I left for a few weeks and I came back. And so it's kind of been on your guys' mind for longer than it's been on my mind. I haven't really had the time to go through and implement everything I want to implement. And there's a lot of stuff there that I need to do. So here, this is the old version of the Cairo library before the other stuff. So let me just do a quick mirage. Temp. Image. 1 second. 0 whatever. .png. And so this visualization isn't the one I wanted to show, but it is kind of a neat visualization, so I thought I'd just show it anyway. This is kind of the Euler method used to solve this particular problem. And basically, as you go further along, and you add more and more lines, so basically more and more approximations, you see the error kind of get larger and larger, till eventually it does this thing. And that's kind of the instability. Okay. One thing I wanted to show for you though right now is going to vi euler.cpp. I'm gonna pop down here, and I want to do visualize Euler ball. Pop up here to the top, right here, go over here and make that. Make that. And let's run Euler one more time, and then I'll show you what I mean. Sorry about that, I didn't realize that, I did not realize that I was not generating the appropriate visualization. So when this one's generated, then I'll show you what I mean. Dagnabbit, segmentation fault. I know exactly why. Because I'm an idiot. Let me just pop this down to 500. Again, I did this incorrectly last time. I know I did, so don't talk about that. Because I know that's not done correctly. And that's something that I have already fixed, but it hasn't quite been implemented on my library either. Not exactly sure what that segmentation fault's for. So let me just go to Euler.cpp and change this guy to 400 by 600. Actually, I think 600 by 400. Now let's run make Euler. Why? GDB. Euler. Run. Backtrace. That doesn't help me. Control D. Yes, let's take a look at Euler.cpp one more time. Change this to 30 maybe. Again, that doesn't really help anything, so not sure here. /Euler. Okay, I'm not really sure what's happening here. So let me just drop the number of frames much lower. Drop this down to, let's just do, I don't know, 300. Make that. Now I'm going to run top over here. And I'm just going to run Euler. Why? Why are you seg faulting? For Pete's sake, I literally just ran that 2 seconds ago. This isn't even the point of today's stream. I just wanted to show something. Gosh darn it. What did it say? It said, Cairo arc, draw field circle. CairoViz.cpp. Let's take a look. CD projects, Simuleos, visualization, Cairo, VI, Cairo, viz.cpp, 185. Cairo arc, what is the problem then? Cairo arc from libcairo 2, draw field circle. Yeah, I'm not exactly sure what this error is. Cairo arc. Okay, well, let me grab another visualization then real quick. Or let me just go into storage, movies, videos, sorry. And then let's go into AAA, Euler. And let me just run Mirage. And I'm going to say it's probably going to be Euler, maybe planets. Is that MP4? Nope. Oh, sorry, MPV is what I want. Yeah, okay, so did you see how right there the planet came in and then it relaxed back down a little bit? That's all I wanted to show, that when I do the visualizations, I typically do that. And the reason being that it kind of makes the planets pop a little bit. And it's kind of useful. Hey, Gothic Death Eater, thanks for coming in. Ohio gozaimasu. Oh, Ohio. I don't know what that kanji reads. I never really know what the kanji reads. Yeah. So I kind of make it grow a little bit and then it shrinks. And I do that with everything. Like all the videos I've ever done. I try to do that, except for with SciVL. When I did SciVL, I wasn't able to manage it because OpenGL was a pain in the butt. So like, for example, when I did the worst sort stuff, let me see, what do I have here? I should have, center worst 1 mpv worst 1.mp4. Let's try worst 2. Actually, what do I have here? Anyway, I've got a bunch of stuff there. Yeah, that's fine. Again, you're implementing it basically the same way I was going to implement it, but that's fine. Okay, so as far as the visualization is concerned, I do want to give the Cinder library a chance because it looks really promising. So let's do Cinder library. Because it actually does work on Linux. That was kind of surprising because I thought when I checked it out a year ago it didn't work on Linux. But I wanted to give this a try too, just to see what happens. And just a bunch of other stuff down there, down that rabbit hole too. Ultimately, guys, I am tired of doing animation on this channel. Like, we've been doing it for like a year now, and I know that that's kind of my shtick at this point, and I hate that it's my shtick because, like, that type of stuff isn't the type of stuff that I started streaming for, you know? I started streaming because I wanted to learn new algorithms and methods and stuff like this. I didn't start streaming because I wanted to make a visualization library. It's just a visualization library kind of became a thing after working on it for so long. And it ended up being that was the main thing I started doing in 2017. And I don't really like spending that much time on it. Like, ideally, I would go back to what I did when I started the stream, which was the moment I start working on visualization or anything that is kind of tedious, that isn't really fun, I don't show that on stream. You know, that was kind of the idea in 2015 when I started. You know, it was like, look, I will do, that's a good going. I think visualization library is coding practice. I understand that, but the thing is, I've been working on it for so long, and I code all day anyway, on stuff that's slightly different and kind of a lot more interesting. And so it's one of those things that, if I'm doing this for fun, why am I spending all my time, like, doing stuff that is kind of boring and not enjoyable to me? You know what I mean? And that was kind of my thing that I was mentioning on Friday, that there are a bunch of things that are very interesting to me, and a bunch of things that are not interesting to me. Things that are not interesting to me, I've been doing a lot of recently because I've been kind of, you know, working on different things. Yeah, I totally agree. I got carried away with it because, again, there aren't really any good libraries out there that do what I want to do, you know? If I want to make a video in generated completely by code, the only other library that does what I want it to do is the Manum library here, which I tried using, but it kept kind of screwing up on me. So I haven't quite gotten it working yet. But maybe I should just use 3 Blue 1 Brown's Manum library. I'm not sure. I'm really not sure at all what to do there. So that's why today I'm just going to go back to Huffman Encoding. We already have a good visualization for Huffman Encoding up and running and good to go. And Huffman Encoding is one of my favorite algorithms, so it should be fun to go ahead and get started and working on that again. By the way, thanks guys so much for coming in. I know I didn't say that today, but thanks a lot. Appreciate it. So let's talk about what Huffman Encoding is, why it's interesting, and where it will go in the future. So let's go ahead and do that. Zernal. Okay, so what I'm going to do first is draw on the canvas, and then I'm going to remove my pen, and I'm going to turn the canvas off. And then I'm going to do that again, because for some reason, again, you guys know the bug, the first time I draw on things, it just doesn't work. And then I'm going to go ahead and pop it over to the second desktop over here, so we have it on the side. Okay, so Huffman Encoding. I covered this like literally 2 years ago. We already had the visualization up. It was one of the first visualizations I ever did on this channel. It's also one of my favorite algorithms literally ever. And I guess, I don't even know if it can be considered an algorithm, but it's definitely a method for data compression. Now, I find it really weird that people don't know what Huffman Encoding is. It's one of those things that I figured everyone would know just because, you know, you take, you know, a couple of math classes and Huffman Encoding just shows up, you know? If you take information theory or data compression, you're probably going to cover a little bit of Huffman Encoding. And so it was one of those things that when I came to graduate school and I started mentioning Huffman Encoding to people, they were like, what is that? You know, they didn't know what Huffman Encoding was. And for me, I was like, what? How do you not know what this is? This is like the coolest thing ever. And so this was kind of one of those first, I guess, little sidetracks I had as a student. that made me realize that maybe my interest is slightly different than the interest of all the other people around me. And at the time, all the other people around me were physicists. So it was one of those things that I really liked. It was a lot of fun. So here's the idea. Let's say you have a phrase that you're trying to encode into a number of bits. So let's say the phrase is very simply A, B, C, D, and you want to turn this into a bit string. Okay, well, the thing is, if your alphabet is, I don't know what twiddle my fiddle means, but it doesn't sound good. A, B, C, D, and you want to turn this into a bit string. Now, the thing is, you want to use the minimum number of bits to represent this alphabet, assuming that no other characters will be added to the alphabet, right? So here's what we have. We have A, B, C, D, and a good representation of this might be 0, 0, 0, 1, 1, 0, 1, 1. Reason being that as long as all of these guys are 2 bits, no matter what bit string you have here, is this an even number? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16. Okay, no matter what bit string you have here, and again, this was just a completely randomly generated, somewhat randomly generated string of bits. This can be turned into a, this can be decoded. So this is A, this is D, this is B, this is A again, this is D again, this is A again. Wow, I'm not very good at these A's and D's. I kind of just made everything an A and a D. This is B again, and then we have D again. Okay, so I've just decoded this. And basically that's because this particular alphabet was created in such a way that there are no repeats. A, B, C, D are all unique entities. Now, let's say instead of using this alphabet, new page before, I wanted to try another alphabet, something like A, B, C, D. Maybe A is just 0. B is then what it was before, 0, 1. C is 1, 0. And D is, let's say, 1, 1. Okay? This alphabet doesn't work. And the reason it doesn't work is pretty obvious. A, being just 0, is also within B and also within C. So if we're going to be decoding a random string, let's do 0, 0, 0, 1, 1, 0, 1, 1, something like this. Well, then this would be A, then A again, right? Or this could be B. I don't really know. If it's A, then the next one here is going to be a D, and the one after that is going to be an A again, then a D again, right? Or it could be B, C, D, right? So we could have this bit string here, or this string here, A, B, C, D. Either of these could be appropriately decoded versions of the string that we read in. So the reason this doesn't work is because this list of code words is not what we call prefix free. That is to say, A is a prefix for B, right? Because the first character in A, the first bit in A is in B, okay? So we have some restrictions on what we can put into our alphabet, of what we can put into our set of code words. The main thing is that the set of code words needs to be prefix free, again, as I just said, but there are a few other restrictions that we'll cover in just a bit. Now, let's say we have new page before. Let's say we have the following phrase that we want to encode. A, B, B, C, 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 D, 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 D. I put these spaces here, but they're not actual spaces in the bit string. It's just 4 characters, A, B, C, and D. Now, let's pretend that we throw all of these characters into a hat, and we shake the hat back and forth, and then we try to pull out a random character. In this case, we have a 10% chance of pulling out an A, a 20% chance of pulling out a B, a 30% chance of pulling out a C, and a 40% chance of pulling out a D. Now here's the thing. In this case, if we want to minimize the number of bits that we're encoding into our bit string, well, we know that we're getting D way, way, way more frequently than we're getting A, right? So it might make sense in the end that our alphabet has a smaller number of characters for D and a larger number of characters for A, right? Because if we just use let's kind of put this out into a table, A, B, C, D. If we use, let's put the probabilities down too. So we'll say character, probability, and let's just do, I don't know, we'll say bit strings 1 and bit strings 2. I know this is kind of a dumb way to do it, but this is what I'll do for now. So we put the probabilities down, so 0.1, 0.2, 0.3, 0.4. And for the first bit string, we can just do what we did before. So 0, 0, 0, 1, 1, 0, 1, 1. And for this guy, let's try something different. Let's try 0, 0, 0, 0, 0, 1, 0, 1, and 1. Okay? So this would mean that because D is way, way more likely, we have it have a smaller number of bits in the end. And because A is quite unlikely, it has a larger number of bits. In this way, we've messed with the alphabet a little bit, but at the same time, this alphabet, this set of code words, is still completely prefix free. And so it should work just fine for decoding. As long as, even though we have a variable number of bits for all of our characters, we should in principle still be able to minimize or still be able to decode any system. Okay, so now the question is, how do we know which set of code words is better than another set of code words? Well, that's actually not so bad. So what we're gonna do is draw in pink because, you know, real men use pink. And, oh, that was kind of sexist. Real women use pink too. Okay, anyway, here's the idea. We can create a character or a kind of unitless value called L, which is going to be equal to the sum of basically the weight times the probability, the probability, let's say probability, times the number of, kind of the length. Hey Kark, how have you been? Let's do nice new room. Yeah, it's been forever, man. I'm glad you're here. So it's going to be the probability times the length of each character. So we're going to say length. Okay, so this would mean that we sum up each of these individual characters here, and I realize I'm notationally wrong here, but bear with me. So we sum up all the different characters in the alphabet, and we basically add the probability, so 0.1 times the length of the code word, so 2 or 3. 0.2 times 2 or 3. 0.3 times 2 or 2. 0.4 times 2 or 1. So let's go ahead and do it real quick. Page, new page before. Again, I'm going to draw the same table we had up there real quick. Ooh, can I? That's interesting. Let me try something real quick. Let me try just selecting this guy. Right? And then doing a quick Control X. Oh, Control Z. Control C is what I wanted to do. So let's go ahead and select this guy. Do Control C. Go up here. Oh, learning how to copy and paste. Boom, look at that. That's... Can I shrink it? If I was using something else, I could. But I don't really know how to shrink it. So anyway, I'm just going to keep this here. So now I'm going to do... Go back to here. Okay, so L1, we're going to say down here, is going to be equal to 0.1 times 2. Right, so 0.1 times 2, the length of the string here, plus 0.2 times 2, plus 0.3 times 2, plus 0.4 times 2, and this is going to be equal to 2 in the end. You can do the math. Encode, nice for me. Hey guys, hey Husky, thanks for coming in. Happy little rat. Nice exclamation marks. I've been fine, thanks. Been working on programming a bit. Is the music changed? Yeah, the music's changed slightly, potentially. Starting in 2018, I just kind of added some new music, slowed it down a little bit, made it a little bit more chill, that type of thing. Power of graphical user interface. Hey, King Frederick. So L1 is this. Now L2, oh, that's not how you spell an L. L2 is going to be equal to 0.1 times 3, plus 0.2 times 3, plus 0.3 times 2, plus 0.4 times 1. Okay? Forgive my horrible handwriting here. Okay, so here's the thing. This guy's obviously equal to 2 because 0.1 plus 2 plus 3 plus 4 gives you 1. You multiply that by 2, you get 2. This guy, so we have 0.3 plus 0.6 plus 0.6 again plus 0.4, and this is going to be equal to 6 plus 6 is 12. Plus 4 gives you 16. 1.9. Okay? So, in this case, we have two different alphabets. I usually play Woodward. No, this is Josh Woodward, actually, Kark. What I did is I took Josh Woodward's entire library. I paid for everything that he had, and then I put it into a music directory, and now I just play it at random, instead of doing what I did before. Wait, what is this? Did you guys hear that they found a new type of black hole? I guess it grows dark red and proves dark matter doesn't exist? Wait, what? That sounds quite the discovery there. I've had lo-fi hip-hop radio on YouTube playing while I work for the past couple weeks. Yeah, I've been doing something similar. I've been listening to like, what is it? It's some sort of jazz. It's like smooth. Let me just see if it's some sort of jazz. Let me think. I think it's a smooth jazz. Nyan Cat? Yeah, this is it. No, I'm kidding. It's background music. I think if I just go to YouTube, I can find it. And let's just go down to subscriptions. Yeah, this Cafe Music BGM channel. I've just been having like the live feed up. So if any of you guys go to this channel in the middle of the day, Japanese time, I will probably have it up. And if you talk in the chat, I might see it and I might respond. So that's how it is. James is the 1st of April. It's Sunday, April 1st here. Well, yeah, it's also Easter. You'd think that Easter would be more important than like, you know, April Fool's Day, but hey, whatever. Got a new keyboard and typing is a struggle. I'm sorry, Husky. I know that feeling. Hey, Lollylol, thanks for coming in. By the way, Lollylol, your name is still hard for me to pronounce. I always have trouble. It's always Lollylol. Every single time. It's just like, hey, lol. Okay. Yeah, okay. But anyway, if you guys are awake, Japanese Standard Time, and you guys just want to chat, I'll probably be in the chat here. But you guys can also chat on Discord, right? Because I'm pretty much always on Discord too. What did I want here? Okay, so here we have the two L's, right? They signify two different sets of code words too. One gives us 2, the other gives us 1.9. And this shows us that with two different sets of code words, we have a measure that allows us to basically tell whether a set of values, a set of code words is more efficient than another one. So that's important because now we have a way to identify which set of code words are more efficient. It's random garble. First ergonomic keyboard I've used, so the shape feels so good, but so foreign. Interesting. Not on the internet. Easter and April Fools. Yeah, so let me get a quick sip of water. My family probably doesn't care about April Fools, but they do care a lot about Easter. Sorry about that. I saw this thing on Reddit where basically it was like on jokes or something like that, and it said, don't forget that Easter and April Fools are the same day this year, so you can celebrate both at the same time by not actually hiding eggs and telling your kids that you did. That way, like, you save work, your kids will be out all the time, like, trying to find eggs, and then you'll be like, April Fools, haha, ha. Yeah, I'm a sad person, I'm sorry, I totally screwed up that joke. That was bad. I should feel bad, but I don't. Okay, so new page before. Let's talk about. So now what we need to do. So now what we need to do is talk about how to generate an optimal set of code words. So we have a condition that allows us to tell what is and is not optimal, and that's important. But we don't have a way to generate an optimal set of code words. And now here's the thing, here's the reason why I love Huffman Encoding. It's not because Huffman Encoding is necessarily cool in and of itself, which it is, but it's because Huffman did this as a freaking school project for graduate school. Okay, so here's the thing. There's some big players in information theory. One guy's name is Shannon, Claude Shannon. If you know anything about information theory, you will know this guy. He's the guy who came up with Shannon entropy. He's the guy that came up with literally everything to do with information theory. You hear about information theory, the first thing you think of, Claude Shannon. He had a disciple called something Fano. Okay? These guys, he came up with a way to generate a set of code words. This guy plus this guy together came up with a new way to generate a set of code words. So let's just put generate set of code words. I'm not actually sure what the hexadecimal there is, but I'm just gonna call you Hex. Thanks for coming in, really appreciate it. So Shannon, again, father of information theory, came up with a way to generate a set of code words. Fano and Shannon together, set of code words. Then came Fano's class. Okay, so here's the thing. Fano was teaching a bunch of people. One person in his class was Huffman. What Fano decided to do was he said, okay, you have two choices for the final exam. What ended up happening, everyone calls me Hex. Hex is fine. So what ended up happening was Fano allowed you to either take the final exam or do a project at the end of the class. And so Huffman was like, okay, I'll take the project because he didn't want to take the exam, as most students would, right? And his project was to generate a set of code words, right? Now, keep in mind, this is just a student in a class. This isn't like some guy spending their entire time researching, like these two people have been doing. So these people have been researching this guy. This guy's just some guy in a class. And Huffman comes up with this way to generate a set of code words that is more efficient and also more consistently generates the optimal set of code words than either of the two predecessors. And again, it's just some random guy in a class. And so it's kind of funny to me that you have some student who just comes up with this idea that completely just destroys two great people in data compression and information theory. And he does it. And from then on, it's always been Huffman Encoding. Because some guy just in a class someday had a cool idea that just beat the snot out of his teachers. You know, in terms of, I mean, not physically, I mean emotionally, you know, I don't know what I mean there. I'm sorry, that was just a bad thing to say, but that's what I mean. I think this is so cool because it's just a student in a class coming up with a good idea, and this somehow just works. And I don't know why I find it so cool, but it is. It's amazing. I missed some chat here. April Fools, not on the internet. Only day when people eat brown things delivered by bunnies and they're happy about it. That's quite good. What did I walk into? Nothing cool. And thus he got an F. No, I think they published the paper. I don't really know what they did after that. Okay, so how does this work? So page new, page before. This is a project called the Arcane Algorithm Archive. The idea is that we will go through pretty much every algorithm in existence, which means we will go through Shannon Fano coding. Fano Shannon coding? We'll go through both of these encoding schemes at some point in time. But for now, we're going to go over the most popular one. And the most popular one is Huffman Encoding. So let's talk about how it works. Let's say we have a list of characters, like we said before. This list of characters will be A, B, C, D, and I'm going to put it up here in the corner. A, B, C, D. We have some frequencies in which they appear, so 0.4. Oh, actually, let me do this on the big screen. So A, B, C, D. And actually what I'm going to do is I'm going to list them in the frequency in which they appear. So it's going to be D, C, B, A. D has a probability of 0.4, C has a probability of 0.3, B has a probability of 0.2, and A has a probability of 0.1. Okay? So here's all we have to do. We basically take the smallest two values at any given moment in time, and we add them together. So in this case, we're going to take 0.2, 0.1, we're going to add them together to be 0.3. Okay? Then we're going to take 0.3 and 0.3, and we're going to add them together to be 0.6. Finally, we take 0.4 and 0.6, and we add them together to 1. Okay? Now we go through the branches. We go back through. And every time we take a right turn, we add 1. Anytime we take a left turn, we add 0. So imagine that we're some guy going back across this way. So we'll say it's a right turn. So we're going to add 0, 1, 0, 1, 0, 1. And this means that D, reading along this line back here, is going to simply be 0. So we're going to say D, 0. C is going to be 1, 0. B is going to be 110, and A is going to be 111. There you go. That's Huffman encoding. All we have to do is go back through the tree, read it up, and we are good to go. And that's our set of code words for this particular, for this set. Now, Huffman encoding is optimal. If you do Huffman encoding correctly, you will generate a set of code words that is optimal for the for your data compression. That's very important because this means that if we're trying to encode anything, we can use some version of Huffman encoding. Not anything, but if we're trying to encode most things, we can use some version of Huffman encoding to cut the bit length down, and that's important. Reminds me a bit of the story where Ian Goodfellow came up with generative adversarial network while in a bar arguing with a friend if it can be done or not. Never make your teacher look stupid. That's definitely something you put on your CV. Yeah, well, he, I think, became a very successful researcher. Actually, I'm not sure what happened to him afterwards. I don't think he did anything that was quite as famous as Huffman encoding afterwards. Let me think. His name is David Huffman. What did he do? See, this is a nice thing about stalking famous people. You don't have to, like, go to Facebook or anything. They're just on Wikipedia, you know? Look, murder. Oh. Oh, that's... Huh. Well, that's something interesting. I didn't know this. Huffman married Phyllis. Yeah, that's fine. Filmography. He's in a lot of films. That's cool. Huh. On the morning of February 27th, 1985, Huffman was fatally stabbed by a suspected burglar in San Diego. The suspected burglar, a 16-year-old named Genaro Samano Villanuevo, I think, probably getting that wrong, has been living in San Diego with family members for approximately 5 months. He had dropped out of high school but re-enrolled and was due to return to school on February 27th. Earlier that morning, Villanueva was taken into custody by police after attempting to steal a radio from a car near his home in India Street. Police released Villanueva, I can't pronounce the name, I'm just going to call him V, into custody of the vice principal of his high school and told him to return to class. Instead, V left the school and went to Balboa Park, where he was spotted by a Canadian tourist, Jack Beamer. Beamer, his wife, and another couple were visiting San Diego and stayed in motorhomes at the park. Beamer saw V prowling around inside his friend's motorhome and yelled at him, causing V to flee the scene. I'm sorry. This is actually very interesting. I apologize for this. At the time of death, David Huffman was appearing in the play Of Mice and Men. What? This guy. This has to be a different Huffman. Oh man, I had this wrong. Oh, this is so embarrassing. It's the wrong Huffman. No wonder this is so interesting. Oh, I was like, who is this guy? That's not the right Huffman. This is the right Huffman. Oh my gosh. Well, can we still go? I'm going to keep going with the story of the other Huffman, but like, this is the wrong Huffman. Oh, what do we have here? I still want to hear this story, but like, this is wrong. Gathros, you probably told me. You probably told me this. Yeah, I'm sorry. I did the wrong. You're right, Gathros. I'm so sorry. Oh. I should have read the chat sooner. Anyway, Huffman was sitting in his van near the theater park of his playing his bagpipes. Who is this guy? He saw Beamer yell at V, then he came chase the vehicle before parking a van near Spreckles Oregon Pavilion. Following Via into the park, Huffman eventually caught up with the suspect, and the two got into a physical altercation during V and stabbed Huffman twice in the chest with a screwdriver. Huffman died of exsanguination, loss of blood to a degree. Okay, that's pretty bad. In 30 to 45 seconds, Huffman's body was found less than an hour. Okay, fair enough. Okay, let's go up to Huffman. This Huffman, who died in 1999, 15 years later. Okay, was a pioneer in computer science known for Huffman encoding. He was also one of the pioneers in the field of mathematical origami. Oh, look at this guy. Look at this guy. I love origami. This is like one of my favorite things to look at. It's like, you know, pretty cool. He got screwed. Oh, that is such a bad joke, but I find it funny. Of Mice and Men favorite books. Okay, so also something cool that we need to cover at some point on the channel. So let's do David Huffman here. Huffman earned a bachelor's degree in electrical engineering from Ohio State University in 1944. He then served 2 full years as an officer in the United States Navy. That's interesting. He returned to Ohio State to earn his master's degree in electrical engineering. In 1949, in 1953, he earned his Doctor of Science in Electrical Engineering at MIT with the thesis, The Synthesis of Sequential Switching Circuits, advised by Samuel H. Caldwell. Huffman joined the MIT faculty in 1953. In 1967, he joined the faculty of University of California, Santa Cruz, and helped found its computer science department, where he served as a chair from 1970 to 1973. He retired in 1994. Oh, nice upgrade. Watch you from the start. So you had a room upgrade. Kind of, it's still actually the same room I've been in. I just added some stuff to it to make it a little bit more soundproofed. Then the origami is the type of stuff you get into to get you murdered. Oh man, I do not want to be murdered. The Wikipedia page is shorter. Oh no, it isn't. Nice upgrade, man. Isley, thanks for coming in. Okay, so one thing I wanted to point out about Huffman, Santa Cruz. There's some guy who comes to OIST all the time. I'm not going to say his name because I don't like outing people who are at OIST too frequently, but I will say that he's kind of an older man. He was one of the reasons I actually was admitted to OIST to begin with. This guy worked with Huffman, actually, and I find that really cool. It's kind of amazing to me that we live in such a small world that, you know, one of the researchers I can meet here at OIST has met and actually worked with for a very long time, one of like the great people who I studied in class, and that's, I don't know, it sounds really interesting to me. The fact that I met someone who did something amazing, you know? And I know that sounds really dumb because all researchers in essence do something amazing, you know, they're all pushing the boundary of human knowledge forward, but it's something about Huffman. I just really like the stuff that he did. And it's pretty cool. Is anyone on Wikipedia alive? Yep, people on Wikipedia are definitely alive. At least so far as I'm aware. Michael? Michael. He's still alive. And then we have, Jesus. You know, he was just born again, you know, yesterday or today, depending on your time zone. So, you know, that's pretty cool, you know. Then we have other famous people like shoot, who's another famous person? 1 second, I got this. I can think of another famous person. Don't tell me. I can think of another famous person. Shoot, I can't think of another famous person. Oh, I know. Gregory House. Hugh Laurie, still alive. I looked at Michael Stevens' Wikipedia page this morning. Coincidence? I think not. No, it is a coincidence. Complete coincidence. Oh, come on, man. Unfortunately not. Hawking. Stephen. I think I spelled that right. Stephen. I misspelled Stephen. That's fine. Yeah. It's okay though. I mean, thing is, this guy's like a bit of a miracle in like this in a lot of different ways. You know, he revolutionized science. He should have died like years ago, but he lasted forever. I mean, lived a good long life, even though, you know, he had major health issues. You know, and I think that's really cool. The fact that he's lived so long, or he did live so long, even though he was, you know, suffering from ALS and stuff. I'm sorry, Lollywall. I'm not trying to stalk you. It just happens naturally. How the F are we going to figure out how to interstellar travel now? It's okay. I'll do it. You know, tomorrow or something like that. Just got to work it out in my notebook. Yeah, here's a notebook. I'll figure it out there. Did you ever read the book Black Hole War by Leonard Susskind? I did not. What's cool about that book? I'm interested. Okay, so let's see. What do we have here? We have all this stuff. spent too long on Wikipedia, as we often do. 50 plus years after expected date of expiration. Yeah, I mean, that's pretty good. You know, like, if I were to eat a loaf of bread that was 50 plus years after the expected date of expiration, I'm not continuing this. I'm very sorry. That was dumb. I don't know what I'm saying. Just forgive me. Ah, crap. I'm sorry. Didn't say that. Keep going. Elon Musk? Oh, wait, what do you mean? He looks pretty conscious. Susskind versus Hawking on the nature of black holes. I actually don't even know Susskind. I don't know many of the, like, here's the thing. If I haven't come across these people in papers, I actually don't know them, you know? Like, it sounds very weird, but like, most celebrities and stuff, I don't know them, you know? Like, the only reason I know Hugh Laurie is because he played in House, and he also played in what is it? A Bit of Fry and Laurie. That was pretty good. It's Susskind's battle with Hawking regarding black holes and whether or not information is actually lost in them. Hawking said it was, Susskind said it wasn't. Oh, that's quite interesting. Listen to us talk. He has a certain Trump feel to his vocab, filled with ums and uhs. Yeah, okay. I mean, the thing is, though, Musk at least can back up what he's doing with something that's useful for humanity. Trump, what did Trump do? I mean, real estate? Something like this? I mean, it's fine, but like, comparing Trump to Musk is like comparing, like, I don't have a good analogy for this, but like, it's comparing like Trump to Musk. It's like, you take someone who's actually trying or actually doing things that are promoting science and education, promoting the world forward, nudging it forward ever so slightly. And then you take Trump, who just like puts his name on things and hopes it sticks. You know, it's kind of like, I don't know. How can information be conserved in a black hole? I don't know. Quite frankly, I'm a bad physicist. Like, I've known this for a while, but I have not been able to look into the, like, for example, relativity. I don't know really anything about general relativity. I should have taken a class on general relativity. I didn't. I know nothing. My quantum information is very poor. I only understand quantum from the papers I've read, and this is coming from someone who studies quantum mechanics in a way, you know? I definitely rate Musk. Just saying he isn't the most pleasing on the eyes and ears. I find it a bit hard to follow his speech. Trump destroying U.S. political deadlock, or while trying to, not intentionally, but it'll all be good in the long run. Yeah, I imagine so. Trump is entertaining, good for relativity and quantum. What do we have here? Open. Oh, I see. I'll take a look at this after stream. I tend to not like to watch videos on stream. Oh, wow. That looks like my watch history is very weeaboo. Okay. So I'm gonna just go back over here. There's a couple things I do want to mention before moving on. The first is that the algorithm archive is a huge project. It's where we kind of put literally everything. I'll go back to Huffman Encoding just 2 seconds. So I wanted to mention this. We are going to talk about mathematics of paper folding at some point. There's a whole bunch of other things that I want to cover at some point. So if you are interested in doing anything, literally anything, any algorithm, any method, anything you want covered, let me know and I will totally talk about that. Or I will totally try to go through that as soon as I can. Again, this is a long project. It'll take some time to go through everything. And of course, I have to research stuff. But if you're interested in something, let me know, because I'm probably also interested in it. It has to be something like programming or algorithmically focused, but, you know, that's the thing. Okay. Let's Huffman Encode Trump. You'll enjoy that playlist. Is the basics of all fields in physics for a layman. Oh, that's quite good. Okay, so one thing I do want to point out is CD projects, Simulaos, Huffman, LS. We actually have Huffman Encoding up and running. Mirage, Huffman .gif. So here's a graphics interchange format file of Huffman Encoding working as intended. Basically taking that long thing that I said before and just doing it in a more animated way. So basically what I did is I took all the characters from Jack and Jill, so Jack and Jill went up the hill to fetch a pail of water. Jack fell down, broke his crown. Jill came tumbling after, and we took them all, put them together, and did Huffman encoding on them. So the sizes of each of the different balls is related to how many times that character is mentioned in the string that we read in. Space is mentioned the most, so it's the highest on the list. Meanwhile, T, exclamation mark, dot, and G are mentioned the least, so they're very low on the list. Yeah, I did this a long time ago, actually. It's been almost a year, maybe 2 years. And so we can do literally any like anything. I'm sorry. We can do any string. We can encode it pretty well with this set or with this code. And so this is kind of some old visualization code I have. And I just kind of wanted to finally put this into a video, wrap it up, and go from there. I'm a big fan of this visualization. It works out pretty well, and it kind of shows you exactly what's happening underneath. Okay, so what we need to do now is write some very basic code to do just about the same thing in maybe Julia or some language that I can put into the algorithm archive very easily. I'm expecting to take till the end of today and most of tomorrow doing this, so I apologize, it'll take some time because I have a lot of stuff that I need to get done in order to get this to work. You did this, what library again? We wrote our own library with Cairo. So this is kind of, so we did a Cairo library a few years back. Then we tried hopping into OpenGL. That one kind of sort of worked. Then we were moving back to Cairo. There's a lot of stuff that we need to get done here. My visualization library is still not complete, and I'm going to try a new visualization library this upcoming week because I wanted something that we could appropriately do 2D and 3D stuff at the same time, you know, and I think I have a library that will allow me to do that. I just have to kind of work on it. But yeah. So this is kind of what we're working up to. If you guys want me to encode something, just let me know and I can just run this code again with a different string and we can do that encoding of whatever you want. In fact, here, I'll just go into the Huffman file right now, .cpp. So if we wanted to do a different string, let's see, what do we have here? I know it's probably in main or something like that. The decoded phrase is, oh, where did I put it? What do we have here? Main. Okay, here's the main, int main, okay. ls, what do we have? Huffman visualization.cpp. This is some old messed up code. That was the binary. Okay. Struct frame, of course. Int main, here we have. So here's our string. So if we change the string, we can do whatever we want. So let me just go ahead and change the string. What do you guys want for a string? std string phrase. Let's just set it equal to something. Just give me a string real quick and I'll encode it. It was in main. It wasn't main, but it was. This is some really messy code, guys. I apologize for it. It's incredibly messy code. So we will encode the phrase it was in main. This is actually a test for me to make sure the code's still working for arbitrary strings. Yeah, it should still be okay. Okay, so we're gonna make that. Vitter. The make file. Back in the good old days. I'm going to go ahead and comment this guy out here. And what I want to do is make the Huffman encoding. So Huffman.o, Huffman.h, bins, vitter. Make clean. Make. I'm not actually sure what's going to happen. So let me just run vitter. Wait. ls. Let's do Huffman viz. I'm actually not really sure what this is going to generate. I've got a feeling I didn't generate the appropriate binary. So let me just go in here and let me go into Mirage frames, image 00000 whatever.png. I'm pretty sure, yeah, this is still the old one. So let me go into the make file again. What do we have here? a.out, huffmanviz.o. Huffman is saved at CPP, animation nothing, a.out. Let's see. So it's already been, so it's been how many years on Twitch? More than 2 years already? Time flies. I remember when you were starting C++. Yeah, kind of. I mean, I was never really starting C++. I was just getting back in the hang of it after using Fortran for years. So like my C++ was really, really, really messy when I was starting, and it was basically C code. It's still basically C code with a few features added in, but it's been a while. Yeah, it's been too long on Twitch. I mean, like, it's one of those things that you kind of think about a lot. I've been here for like, I'm not going to be able to stay on Twitch for too much longer is what I'm saying. I don't have too much time. Oh, what is screwy? Man, this brings me back. Look at those colors. Beautiful. Yeah, there was like an integer division problem or something like that with this that took me forever to figure out what the problem was. But I think it happened around Christmas one year or something. So like it was like one of those like kind of flashy animations that I don't remember. It's been forever. Okay, I want to just very quickly make this real quick. So let's go into VI makefile again. Huffman.o, Huffman viz. What I want to do is XX. Yes. Make. Final tree was not declared in the scope. Let me think. Huffman viz CPP error expected. Yes. So let's go into viz.cpp and go into 112. And this is because I must have forgotten to put a semicolon. Make that. Okay. Now what we're gonna do is very quickly run. I want to say Huffman viz. Yeah, this should work. Okay, and then we'll run the last, well actually a few mirages up. Here we are. Okay, so we should have, yes, so there's our new tree. And as you can see, the tree changes based on what we read into the system. So here we just put in the phrase, it was main or something like that, it was in main, whatever it was. And then there we are, new tree, new bit strings. And as we mentioned before, the bit strings are dependent on what we read in, so the space was used most frequently, so it has the shortest code. Meanwhile, all of these letters were used with the same frequency, so they have the same code length. Basically, the depth of the tree that you go down will be the length of the code word that you're reading out. So that was something I wanted to show there. Okay, cool. So let's go ahead and do some writing. It didn't go on that new line. Yep, I got it. It's fixed now. Thanks, Nemi Games. Appreciate it. So now what do I want to do? I want to go ahead and CD back over here. And let's think, how do we want to do this? What I need to do is write some code for the algorithm archive. So I'm going to go ahead and CD into projects. And I'm going to put it in Simuleos for now. But we're going to move it to the algorithm archive in a bit. This will be some example code. And I'll be honest, I haven't actually written out the example code yet. So it could be that when I write this example code, there's some things that I just kind of forgot about that I need to think through as we're going through it. So if there's anything that you want to say, talk about in the chat, feel free to let me know, and I'll totally address it as soon as I see it. So CD projects, Simuleos, CD Simuleos. And you know what? I'm actually going to put this in the same directory we were just in. So let's go ahead and CD into Huffman 2. Do a quick ls here, and CD into Huffman. Okay. Good, this is working okay. So I'm going to go ahead and create a new file, huffman.jl. Now, let's think about what we're going to need. We're going to need a couple functions in here. Now, in the previous code that we have, let me just go into vi huffman.cpp. We had a number of different, let me go to huffman.h. Okay, so we had a number of different things here specifically for visualization. And this is one reason why I wanted to have a new visualization library, because every time we had to do visualization with the previous visualization library, it got messy. Like, it got messy really quick. So let's see, what do we have here? For the actually necessary functions that we have here, we have Huffman, we have create bits, we have encode, we have a depth first search, which is actually pretty necessary for this case. We have 2-pass Huffman and decode. Okay. So what do we have here? We have Huffman tree here. So we're gonna have to have some sort of struct, which is going to hold basically all the information that we want here. Now, here's the thing. This is going to be done in Julia instead of C++ for the example code that's going to be put on the algorithm archive. So I'm trying to think of, I need to write something that is clean and easy to read. So if you guys are having trouble following anything that I'm doing, let me know. And I will try to, I'll try to fix that as soon as I can. One final thing to note, let's go into algorithm archive, which I think I have over here. And let me go into tree traversal. Where is that guy? Tree traversal. So the algorithm archive now obviously can hold, or if you guys haven't seen it in a while, you can flip between all the different languages. It's looking pretty good. It's pretty effective. We're going to basically create a tree in a very similar way as we did over here. So we'll have some sort of struct node. In Julia, you always capitalize the name of the types that you're creating. So it'll be something like this. Now it's always going to be a binary tree. So we always know that the node inside the node is going to be either left or right. There's no reason to have like a vector of nodes inside. So let's go ahead and just start writing something. So struct node. Now over here, I called it Huffman tree, but this is slightly different. And then we're going to end here. In here, we're going to have some sort of node right and left. And we're also going to have a few more things. Now, the reason I have this up over here is to see what else we need, because I don't actually remember all the stuff that we need. So over here, we have a node star root. Oh, you are totally right here. We have an additional, my bad guys. We have an additional bunch of guys here. So inside the node, we have a bunch of different things. So we have a weight. Let's just go ahead and do, oh, that's not how you define things in Julia. One of these days, I will remember how to code. That is not today. Okay, so now we have a weight, which is just going to be a float 64. Okay. On top of that, we're going to have some sort of position, but the position is just for visualization, so we don't necessarily need that. Yes, root is just the first node. That's what I kind of realized as I was going through this a second ago. Our Huffman tree down here is basically holding the final result before decoding. So we basically just store the root node, and then we go through and go from there. So that was the thing I needed to mention there. That the Huffman tree kind of like just the data structure that we pass on to the encoder and decoder. It's not necessarily where we hold the node itself. So, and we also need parent. Okay, so we have the weight here. Anything else we need? We probably need a character, which is the key itself. Yep, that should be okay. Now let me think, how do we do this? So let's do key. Now what is character in Julia? 1 second. I think, is it just string? That, of course. Strings. I guess we just do string. Char. Of course it's char. Okay, so that will be our struct for our node. Now we need to basically create the struct for the tree itself and a few other things. Now let me think. This got really complicated really quick, and I don't remember why it got so complicated. So I need to kind of take a look at it and figure out that too. So it's going to be kind of, how do I put this? There's going to be some of me trying to figure out exactly how to implement everything. What I'll probably do is I'll probably get some basic stuff written down, and then we'll end at 6:30 today, I think this morning. And then I'll spend the other 30 minutes on my own time writing down the pseudocode for this, so that when we pop in tomorrow, the first thing we can do is do a very brief introduction of Huffman encoding, nothing as long as like what we did today, and then after that we can hop right into the programming. And so I think that's how I'm going to do it today, or how I'm going to do it. With the pseudocode, we can go through much faster, and so that way we can finish roughly on time. So I'm going to say probably Tuesday or Wednesday we'll be finishing. Okay. So no, the next thing we need is some sort of Huffman tree itself. So let's go ahead and do that. Struct Huffman tree, and the struct down here. Now the thing is, everything's always capitalized. So let's see what happens. So we're gonna have some sort of node root. Come on. What else do we need in here? I have an unordered map of string and then of characters and strings. That seems to work okay. Then we have phrase and encoded phrase. Then we have a weight map, which is again another map with a character and all their weights. We have an alphabet size, all this kind of stuff. So go ahead and put all that in there. Again, this is all for encoding and decoding. There's probably a much more efficient way to do this. I just need to think it through and figure that one out. So let's go ahead and do, let's see, how do we do maps in Julia? Man, I'm so bad at this. Freaking everything. I just don't remember how to do it in Julia. So maps, Julia. Why? Why is literally everything not what I want with Julia? Like, linear maps, color maps, map visualizations. No, I just want map data structure. Unordered map. Mundo goes where he pleases. What algorithms would win in the stock market? Huffman Encoding. I remember having to implement this in x86 assembly for an assignment. Yep, I'm sure you did. You're better than I am. Mundo, wait, what algorithms would win in the stock market? There's actually algorithms for this. I think they're called stopping algorithms. One second. Optimal stopping. And I want to say stocks. Option trading. Yep, here it is. So there's actually some stuff here if you're interested. Control C. Wait, gross? What? What's gross? Oh, what yak said. Okay, so let's go and keep going through here. I have to remember how to do maps in Julia. I should have just written out the pseudocode before I did this, but I was kind of spending all day yesterday, again, writing the data compression stuff over here, so I didn't spend as much time writing the pseudocode as I probably should have. That's okay. It is what it is. So maps. Linear maps. Map in Julia. Oh, it's probably a dictionary. I'm trying to geographical map in Julia. It's probably just a dictionary. So let's say dictionary. Dictionaries and sets. Good. String integer. That's what I want. Fantastic. So let's go down here and let's go ahead and add that in there too. So we're going to say bitmap. And this is going to be a dict between. Let me see. I remember when I programmed Huffman, I used the canonical encoding. I didn't require a dictionary, from what I remember. You know what? Fine. Let's go through here, and let's think about what we actually need. Because this guy over here we wrote a while ago. It's some good old-fashioned C++ code that is probably a little bit too complicated for what we need it to be. So let's talk about what we actually need. Page. Oh yeah, it's fine. Doesn't matter. Okay. So for Huffman encoding, here's the things that we definitely need. Huffman encoding. Okay, we definitely need some sort of list of nodes, right? So we need a node, and inside of the node, we're going to need, again, left, right, and parent. So I'm just going to do left, right, parent. LRP will be fine. Each of these guys has to have some sort of weight, which is associated with the probability, and it has to have some sort of character. Okay, good. We know that this has to be in the node. Fine. As with all algorithms, it doesn't matter what language it is. It just takes a little while longer. That's true. The thing is, when it comes to implementing different, it depends. But sometimes when translating from one language to another language, it's much, much harder. Translating like from, for example, MATLAB to literally anything else is a pain in the butt. But translating from like Julia to C isn't usually so bad. The advantage of the canonical encoding is it doesn't require to store a dictionary with the data. I found that on a web page, and I think it was the only one you could find. Yeah, let me take a look at this then. Canonical Huffman encoding is a particular type of Huffman encoding with unique properties which allow it to be described in a very compact manner. Data compressors, there we go, generally work in one of two ways. Either the decompressor can infer what codebook the compressor has used from previous context, or the compressor must tell the decompressor what the codebook is. Since the canonical Huffman codebook can be stored especially efficiently, most compressors start by generating a normal Huffman codebook, then convert it to a canonical Huffman before using it. I see, okay. In order for a simple code scheme, such as the Huffman code to be decompressed, the same model that the encoding algorithm used to compress the source data must be provided to the decoding algorithm so that it can use it Man, I cannot read today, to decompress the encoded data. Instead of Huffman encoding, this model takes the form of a tree of variable length codes, with the most frequent symbols located at the top of the structure and being represented by the fewest number of bits. However, this code tree introduces two critical inefficiencies into an implementation for the coding scheme. First, each node of the tree must store either references to its child nodes or the symbol that it represents. This is expensive memory usage, and if there is a high proportion of unique symbols to the source data, then the size of the code tree can account for a significant amount of the overall encoded data. Secondly, traversing the tree is computationally costly since it requires the algorithm to jump around randomly. Interesting. Okay, so here's what I think we should probably do. We should have a simple implementation of Huffman encoding, like say, hey, this is the naive way to do it, and then maybe we go here for more information on the canonical stuff. This seems actually quite interesting. I kind of want to look into it. Method for construction of a minimum redundancy codes, David Huffman. Interesting. The invention, let's see. Now there's several pages on it. Hey all, what's up? Hey Galvabart, thanks for coming in. Can you use a public class inside another private class? I'm not... No, I'm not sure. I haven't actually tried it. I don't know offhand. Okay. So what I need to do is look into this, and I also have a list of other things that I need to do. Okay. Well, this is good then. We have a list of things to look into, and I'll try to do it today to get more stuff done after that. This Wikipedia page didn't exist at the time. Fair enough. Okay, encoding the codebook. The whole advantage of canonical Huffman tree is that one can encode the description, the codebook, in fewer bits than the fully described tree. Jeez. Let's take a look at let us take our original Huffman codebook. There are several ways in which we could encode this Huffman tree. For example, we could write each symbol. Yep, fair enough. Since we are listing symbols in sequential alphabetical order, we can omit the symbols themselves. Yep, that's fair. With our canonical version, we have the knowledge that the symbols are in sequential alphabetical order, and that later code will always be higher in value than earlier ones. The only parts left to transmit are the bit length numbers for each symbol. Note that our canonical Huffman tree always has higher values for longer bit length, and that any symbols of the same bit length, C and D, have higher code values for higher symbols. You can create a class inside another class. The public type limits what can be used within the class. Okay, so this is definitely a lot of information that I need to go back through. Okay, so let's talk about what we need for a naive implementation of Huffman encoding. Then after that, I'll take a look at this canonical stuff one more time, see what we need to do there. So again, for Huffman encoding, we know that we need a node, and these nodes will make up the basic binary Huffman tree, right? So we know that. We know in the end, the easiest way to implement a Huffman tree is going to be with some sort of priority queue of all the nodes, so we're going to need that. So we're going to say priority queue of the nodes. And basically the reason we want this priority queue is so that we have a list of all the nodes based on their order. So in case you guys don't know, which I'm sure most of you guys do, the priority queue is just a queue that in a sense automatically sorts all of the nodes in the order of, in some order. And here we'll make the order based on the weight of each node. So the priority queue will be based on the weight here. The reason that it's important is so that we always know which variable is in which order. So for example, when we were drawing the Huffman tree before, it's very important to know that the 0.4 is on top and the 0.1 is on bottom. So it's very important to keep this order. Otherwise, Huffman encoding doesn't quite work. So we're definitely going to need that priority queue. Now we need some way to represent the list of code words, right? So now we need some sort of map, I would say. And it doesn't necessarily need to be ordered, so we're going to say a map of code words. Let me rewrite that because that was just horrible handwriting. Okay, so we need a map of code words. This is basically going to be taking each of our characters here, and it's going to be saying that the character is going to be related to some bit string, right? So we're going to say this character is 0, 1, this character is 1, 0, something like that. So we have the priority queue of nodes, a map of code words. What else are we going to need here? We're going to need some way to encode and decode. Now, once we have the map of code words, it's actually not so bad in order to encode and decode. So encoding is just basically taking whatever character we read in, going through the map of code words, and the other one's just going the opposite way. So then we just need an encode and a decode. Okay, so this is basically all we need. Oh, 1 second. So we need some way to create the Huffman tree, which will basically be, first of all, going through the characters that we have. So we go through all the characters, right? So if we get the word hello, we read through all the characters and we figure out the probability of finding any of the characters, right? And then after that, after going through all the characters, finding the probability, we then go through and encode it. So that's kind of why it's called, I didn't mention this before. So we go through it once to find the probabilities, then we go through it again to do the encoding. So because we go through it twice, this is why it's sometimes called 2-pass Huffman encoding. Now, as I mentioned a long time ago, there's actually a bunch of different ways we can do the encoding. We can do 2-pass Huffman encoding, which is the easiest way to do it. We can also do dynamic Huffman encoding, such as the Vitter algorithm and a bunch of other things here, which again are things that I'd like to cover in the future. It's just there's so much stuff to cover. It's one of those crazy things. Like, this is kind of why I hate the fact that I spent so long doing visualization, because like, yeah, in some sense it's kind of nice, but on the other sense, there's so many algorithms to cover. It is just impossible to go through all the algorithms, do appropriate visualization of all the algorithms. Like, it's definitely one of those things that's like a full-time job that I just don't have time for. Man, there's so much to cover, even in this little area right here. I can just think of like 5 or 6 algorithms I want to cover, like just right here in this little area of data compression. I know, like, I didn't mean all of data compression. I just mean like just here around Huffman encoding. There's Huffman encoding, 2-pass Huffman encoding, dynamic Huffman encoding, the Vitter algorithm. There's Fano and Shannon encoding too. Like a whole bunch of different things here to deal with entropy. It's just so many things. But here's the list of all the things we need for Huffman encoding in a basic implementation. Now, for what Lollylol mentioned a while ago with the canonical encoding scheme, I'm actually not sure I fully understand how the canonical encoding scheme is different than the encoding scheme I currently have up. And it is kind of 6:30 in the morning my time. So I think what I'm going to do is do what I said just a second ago. So today was kind of the overview of what Huffman encoding is, a basic introduction, nothing more than that. I think tomorrow we're going to go through and actually get all of the code done. So I'm going to probably end stream pretty soon. Write down a list of everything I want to get done, basically write down the pseudocode for what we're going to write, so that tomorrow we can just hop in and just immediately start programming in a quick, concise manner without any of the ums and ahs that you guys are used to in the Simuleo stream. I really want to start like refining the stream, making it kind of cleaner, crisper, less of the kind of figuring out implementation details and more of the I have a clear goal for what I want to do today type of thing. So that's kind of the hope for the next week, kind of ramping myself up for that kind of thing. And so with that, I think we're going to go ahead and close for the day. I realized we didn't actually implement very much, and I apologize for that, but we do have a good list of things that we need implemented. We have an idea of where we want to go, and we have 2 different methods that we want to implement for the first bit of Huffman encoding. So the schedule for this week is going to be as follows: new page before. Okay, so let me just go ahead and write down the schedule. Today is Monday my time, so I'm just going to go ahead and put down Tuesday, Wednesday, Thursday, Friday, and here's the goal for the rest of this week. Tomorrow I want to spend the whole time implementing basic 2-pass Huffman encoding. Now, I suspect we're going to run into a problem, and this will probably bleed into Wednesday. So I'm going to say finish up 2-pass here. So 2-pass is also going to be done here, so 2-pass. Then I'd like to spend some time here talking about the canonical stuff, because I'm not sure how that works, and I'm not sure how that'll go. So I want to spend probably half of Wednesday and half of Thursday doing canonical stuff. Good. So I'm going to assume we're going to be done with Huffman Encoding here. And then I want to spend some time just going through basically the Cinder tutorial, because there's some really cool stuff there. So let me try to hype up Cinder really quick, because it's something that I don't think, I mean, Gustor knew about it a long time ago, and I kind of said no a while ago because it just seemed too complicated then. But now that we've got some OpenGL under our belt, I feel like it's going to be quite good. Oh, I already have it up. So here, if we go to, I guess, Learn, and we go to, not Setup. No, that's not what I want. About 3D graphics, library. What am I looking for? I'm looking for, come on. Maybe it's here. Download, sponsors. I can't find it actually. But basically there's this documentation stuff that we can learn here. And when we go here, here it is. OpenGL and Cinder. That's what I wanted. Okay, so here's just a basic introduction to Cinder is what they say. And after looking at this, I was quite excited to try this out, because in the very first example, so here's just getting started, like the hello world of Cinder. Like, look at this, they already have this. This is quite cool. I don't know what this is, but like they can do a lot of stuff. Adding in the third dimension seems relatively straightforward. Much easier than whatever I was trying to do with OpenGL. You have 3D cameras, so you're able to move things in and out, which means it kind of beats the snot out of VTK, which is the other thing I was planning to use. I mean, look at this. That's so cool. It just seems, like there's a lot of stuff here to do. So this is why I'm trying to hype it up. Hopefully we'll have something that we can do that we find interesting here. So I'm hoping that this allows us to do more stuff. The other thing that's cool about Cinder is it actually allows us to immediately take whatever we want and put it into video. And that's nice, because this is something I wasn't able to do with OpenGL very easily. Also, this song. I'm sorry. But that's it. So this is not the song I want to be playing when I'm trying to hype something up. It's like the opposite of hype. It's like the la 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 la. Okay, so this is where we're heading. So again, I think that's a good schedule. Tomorrow we'll spend the whole time implementing basic 2-pass Huffman encoding. Probably going to bleed into Wednesday. Wednesday we'll start working on the canonical stuff, as Lollylol mentioned. That'll probably take to Thursday. I will write the algorithm archive article on Saturday, hopefully do all the video editing and all that kind of stuff. So I'll write the script on the side. And what's the other thing I need to do? And then I'll look into this libcinder stuff. It'll probably just be us following the basic tutorial, nothing more complicated than that. And that'll be it. Okay guys, so that's it for the day. Thank you so much for coming in. Have a great day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you around next time for the next episode of Simulaos, when we actually get down and dirty with 2-pass Huffman encoding, getting it basically written down. I'll do a quick introduction, but it won't take nearly as long as it took today. So this will be the, I guess, go-to video if you want me to go back through Huffman encoding until I write it up in the algorithm archive and make a YouTube video about it. Thanks again guys so much for coming in, and I will see you next time. Bye guys.